Hello and welcome to Circular Motion 4 with me, Mr. McIver, here at the London Central and Northwest Maths Hub. Lots of thanks to give today. Dr. Michael Gallis of Penn State for his Loop the Loop animations, Dr. Boyd Edwards of Utah State for his ball and a string, and Mr. Ingle of Dr. Frost Maths for their help with the slides. Today we're looking at vertical circular motion. First of all, a quick recap of what you need to know. I'm presuming you already know everything about horizontal circular motion, and in particular, circular motion with constant angular velocity. To make sense of stuff in a vertical circle, you also need to be familiar with these two equations, which I'm sure you are. So let's move straight on to vertical circular motion. And we're going to start by looking at a car looping the loop. Let's pause this video here to talk about what exactly is being shown on this screen. First of all, look at the car itself. You can see the weight of the car being shown as a vector, that's the yellow arrow pointing vertically downwards, and the normal reaction of the track on the car being shown by that blue arrow pointing upwards, rather unhelpfully being described by the letters FR, but that is the normal reaction. Up in the top right-hand corner, you can see the speedometer, showing that the vehicle is going at 11 meters per second. And for your information, it's heading towards a loop of radius 12 meters. The other things being shown in the top right-hand corner are the kinetic energy, illustrated by the green bar, and the g-forces being experienced by the driver, shown by the yellow. The one I want you to look out for is the blue bar, which will shortly appear between those two, showing the gravitational potential energy of the vehicle. So let's restart the video. And as you see the car going round the loop, the gravitational potential energy goes up while the normal reaction drops to zero. Then the normal reaction picks up again and the gravitational potential energy goes back down. Finally, we can see that when the car has got through the loop, the weight and the normal reaction are perfectly balanced as they were at the start. So now let's take a closer look at what's happening there theoretically. So here's our vertical loop. We're giving it a radius r because we want to look at the general case here. We'll put the car on the track, but we'll model it as a particle with velocity v, strictly speaking, tangential velocity v. And because it has that tangential velocity, it is therefore accelerating towards the center of the circle at a rate of v squared over r. Now, in order to maintain the circularity of the path, the track, therefore, has to be delivering a normal reaction of ma, that's mv squared over r, towards the center of the circle. But that's not all of the normal reaction, because, of course, this car also has a weight. It's got a weight of mg. And because, on this part of the track at least, a component of that weight is drawing it in towards the track must also be delivering a normal reaction equivalent to that component of the weight acting towards the center of the circle. So, at this point on the track, the total normal reaction of the track on the car is given by mv squared over r, the force required to keep the motion circular, plus the component of the weight. Now look at what happens when we get to the very top of the circle. Once again, we have our car of mass m moving with velocity v and therefore accelerating at v squared over r towards the center of the circle. The force the track must deliver to maintain that circular motion is therefore that mv squared over r as before, but now the weight of the car is effectively taking away from the normal reaction, delivering that acceleration. In other words, if the velocity isn't big enough and the force required to deliver that circular motion isn't as big as the weight acting downwards, it'll fall off the track. And in fact, the way I've drawn those two arrows, it looks like it is going to fall off the track. But the important thing to understand is that when you are considering the normal reaction at the very top of a vertical circle, at least for a loop-the-loop situation with the car inside the circle, the normal reaction is given by this. mv squared over r, that's the force required to deliver the circular motion, minus the weight. Contrast this with what happens at the bottom of the circle. Once again, we have mv squared over r acting towards the centre of the circle, preserving that circular motion. But of course, the mg is still acting vertically downwards, which means there will be a corresponding normal reaction also acting towards the centre of the circle. That means that the total normal reaction at the bottom of the circle is that mv squared over r plus mg, a much larger number than the normal reaction at the top. So, if you are travelling round a vertical circular loop at a constant speed, you will feel a lot heavier at the bottom of the circle than you do at the top. Okay, let's have a look again at our particular case of a 12-metre radius loop and a car travelling around it. What is the critical velocity required to keep the car on the track? What's the minimum velocity you need to be going at to avoid dropping off before you get to the top? Well, the normal reaction at the top of the track is given by that. We've already figured that out. And in order to preserve circular motion, that must stay above zero. Theoretically, it could drop to zero. But that is the borderline case. So all we need to do to find the minimum velocity required is solve that equation for r equals 12. Well, we can take out a common factor of m and divide it out. That means v squared over r minus g equals 0. So v squared over r has to equal g. You rearrange, you get v squared must be greater than or equal to gr. We sub in r equals 12 and we get a minimum velocity for making it round that loop of 10.8 meters per second. So, yep, our model showed what does happen. 11 meters per second is just enough to keep it on the track. But as the simulation showed, the normal reaction dropped to very near zero at the very top of the circle. Now let's see what happens below this critical speed. I want you to pay particularly close attention to that yellow G's bar in the top right-hand corner, because that measures the normal reaction. Here goes the car, and as you can see, the normal reaction builds up when it hits the track, then it drops and drops and drops and drops, and oh my goodness, the G's have dropped to zero, and it leaves the track. Oh dear, not a good result. Interestingly, this situation of a car falling off a vertical loop when the normal reaction reaches zero is precisely analogous to the situation of a ball on the end of a piece of string failing to complete a vertical circle when the tension in the string reaches zero. So let's go back to our vertical loop. This business of travelling around at 11 meters per second is starting to look a little bit dicey, because a fraction slower and you're going to have a horrible accident. So wouldn't it be more sensible, if this was a real fairground ride, to go quite a bit faster, say 20 meters per second? Give yourself a bit of a margin of error just in case things slow down a bit. That sounds all very well. So let's have a look and see what happens to the rider travelling round at a speed of 20 meters per second. Remember that the normal reaction at the very bottom of the circle gives you the maximum g-force the rider will experience. So let's just see what happens at the bottom of a circle of radius 12 meters when you're in a car going at 20 meters per second. We simply substitute in r equals 12 and v equals 20, do a quick calculation, and 41.3 m is our acceleration. If we divide that through by 9.8, we come to the conclusion that's 4.4 mg. That means if you took the entire loop at 20 meters per second, you would be experiencing a body weight 4.4 times greater than you usually do. Well, that might not seem too bad, but of course you have to remember, roller coasters don't actually work like this. Generally, when you're on a roller coaster, the whole thing coasts. That's why it's called a roller coaster. You just start up at the top of a great big hill, get faster and faster and faster and faster, and then the kinetic energy you have at the bottom of that loop is enough to carry you all the way around to the top and keep you on the track. Well, supposing you wanted to coast through the top of that loop at 20 meters per second. How fast would you need to be going at the bottom of the loop, and what g-forces would you experience? Let's try to work this out using energy. The energy at the top of the loop has to be equal to the total energy at the bottom of the loop. In both cases, it's kinetic energy plus gravitational potential energy. And the total gain in height as this car travels round in a circle is simply twice the radius. So we get that formula for the energy at the top of the loop, a half mv squared plus 2rmg. We substitute in r is 12 and v is 20, and we get that, 435.2 m. Using conservation of energy, we must have all of that energy expressed as kinetic energy at the base of the loop. So we simply equate a half mv squared to 435.2 m. That's quite an easy equation to solve. We get a velocity of 29.5 meters per second. Well, fast, but only exciting, not mad. But let's see what happens when we turn this into an acceleration, 8.4 mg. Now, just to put this in perspective, top fighter pilots are trained to withstand g-forces of up to 9g, if they're really good, without blacking out. No ordinary person would be able to endure those kind of forces. They'd be liable to black out and then be violently sick when they came to, which is not a great experience when you're on a roller coaster. This is why real roller coasters actually look like this. They're not circular. This was the tallest vertical loop roller coaster in the world when it was built at 49 meters from top to bottom, and you can see quite clearly that this isn't a circle. The radius at the top of the loop is smaller than the radius at the bottom of the loop. This is because you want to maximize the g-forces at the top for a reasonable speed, ensuring that the roller coaster doesn't fall off the track. But you want to open out the radius at the bottom to reduce the g-forces on the passengers. So to recap, here are the ideas we've looked at in this video. Central to our whole approach was the idea of conservation of energy, or the so-called work energy principle, which states that work in plus initial KE plus initial GPE equals final KE, final GPE, and work out. This actually simplifies in our case, because in all the situations we're going to be looking at, there is no additional work going in. So we can dismiss those two terms and simply end up with KE plus GPE before equals KE plus GPE after. That is at the heart of everything we're going to be looking at with vertical circular motion. But of course, we mustn't forget the basic horizontal circular motion stuff we did before. So the second big idea to recall is that radial acceleration combined with F equals ma, Newton's second law of motion, are still core to our modelling approach. And while we're on the subject of models, let's just remind ourselves of the situations we can model given what we now know. We focused today on a car looping the loop, but we did point out that in fact mathematically exactly the same model describes a ball on the end of a piece of string. You also need to be aware of another, actually simpler model, which is some kind of mass on the end of a light rod. The only way something doesn't complete circular motion is if it falls back down, because a light rod can't go slack, it just won't make it round the circle. So that's actually a simpler situation to deal with. And that's it for this lesson on circular motion.